And let's get to it. Okay, section 17.7 deals with the reduction of benzene. And if you're wondering, could you hydrogenate benzene? Could you hydrogenate all three of those double bonds? The answer is you can do it using three equivalents of hydrogen and, of course, a catalyst like nickel, palladium, or platinum. But you can see that it requires really high pressure and high temperature. So kind of dangerous chemistry, but it can be done. Now, if you use the more traditional reduction conditions that we're used to, where you take an alkene and you hydrogenate it using hydrogen gas, palladium, platinum, or nickel, it says only 2 atmospheres here. That's not very high pressure, and this is at room temperature. If you have an alkene somewhere else in the ring, you can reduce that selectively and leave the aromatic ring intact. So that's pretty cool chemistry. You could take styrene, this compound here, and you could convert it into ethylbenzene, shown here. So kind of interesting chemistry. But what about other means of reducing an aromatic ring here? And it says that benzene can be reduced via a Birch reduction. And Birch is somebody's name. It's a chemist by the name of Arthur Birch. And yeah, so we've talked about sodium metal reduction way back in chapter 9.5 when we were talking about reducing an alkyne. So if we took an alkyne and we treated it with sodium metal in liquid ammonia, we could make a radical cation and make a transalkene. But now we're talking about taking an aromatic ring and reducing it in the presence of sodium metal with ammonia, but we also have methanol. And if you're wondering, what's the methanol for? Well, we're going to talk about that in a second. And instead of making, a transalkene, now we end up with a 1,4-cyclohexadiene. And the mechanism of this reaction, this Birch reduction, is actually somewhat similar to the reduction of an alkyne that we saw in chapter 10. Let's take a look. If you think about where sodium is found in the periodic table, sodium is in group 1A. Group 1A, we find sodium, and that means that sodium has one valence electron, and it likes to lose that electron. It has a low electron affinity, and so it can lose that electron. It can transfer it to the aromatic ring, and you see some really interesting curved arrows here. We have a total of 5 fishhook arrows here, and we end up with, hey, a radical anion. And you would remember seeing the radical anion in chapter 9, which helped us understand why we end up with a transalkene. Well, now you get a radical anion. And the anion ends up pulling a proton off of methanol, which is in our reaction mixture, and then you end up with a radical. So where does the other proton come from? Well, check this out. Since we're in sodium, sodium can donate a second electron, or another atom of sodium, I should say, can donate a second electron so that we end up with an anion. So in the first phase, we have a radical anion. Now we have an anion, and the anion can pull a proton off of methanol. And so we end up getting 2 protons ripped off of the methanol, and now we have our 1,4-cyclopentadiene. Pretty interesting chemistry. Well, what I want you to be reminded of, and I think this is a mechanism you should know, so let's put that in here. Know this mechanism. Move that bus, okay? So I want you to know this mechanism, and notice that we end up forming an anion twice in the mechanism. We form an anion when we form the radical anion, and we form an anion in the second phase of the mechanism. And there's going to be some interesting consequences based on this anion when we look at the regiochemistry of a Birch reduction. The Birch reduction does not completely reduce the entire benzene ring, but rather it has 2 nuc sp3 hybridized carbons, and they are on opposite ends of the ring to each other. You could almost say they're para from each other in a way. It's not really a proper use of the word because it's not an aromatic compound, but anyhow, you could think of it that way. All right, well, let's take a look at regiochemistry. It says here the presence of an electron-donating alkyl side group provides regioselectivity. For electron-donating group, I like to use EDG, and electron withdrawing group, I like to use EWG. But remember that an alkyl group is electron donating through hyperconjugation. Now, I'm not going to ask you to write an essay about hyperconjugation, but I want you to know that an alkyl group pours electron density into the ring. It's electron donating. And therefore, when you do the reduction, the carbon where the alkyl group is substituted is not going to get reduced. Why? Because if you think about it, the carbon that gets reduced, both of those carbons end up getting reduced. At one point, those were both anions. Look back at the mechanism. Here's an anion, it becomes an sp3 hybridized carbon. Here's an anion, it becomes an sp3 hybridized carbon. So why would you want to reduce a carbon that already has something that's donating electrons into it? It's not going to want to have a negative charge and have electron density poured into it. Put another way, an electron donating group destabilizes the radical cation, and so reduction doesn't occur at a carbon possessing an electron donating group. However, what if we do have an electron withdrawing group? Well, electron withdrawing group is going to do the converse of an electron donating group. It's going to withdraw electron density away from the ring, and therefore that carbon is going to be reduced, the one that has the electron withdrawing group on it. Why? Because the electron withdrawing group is going to stabilize the intermediate anion that's formed along the way. And so we wouldn't get any of this compound. However, the carbon that does have the electron withdrawing group on it is going to be reduced to an sp3 hybridized carbon. And there we go. So that covers the regioselectivity of Birch reduction. Electron withdrawing groups, their carbons get reduced. Electron donating groups, their carbons do not get reduced. Well, with all that in mind, let's turn our attention to some synthesis problems here. 17.18, none of these deal with Birch reduction. We'll talk about that in class on Wednesday, but I wanted to try a couple of synthesis problems here that deal with some benzylic chemistry. So I'm just going to go over to a blank document here quickly, scribble these down just so I have enough blank space. There we go. So let's see. This is question 17.18, and we're starting with just toluene. Oh, this is 17.18C. We're starting with toluene, this compound, which is an aromatic compound. And we want to convert it into this interesting looking nitrile here, where we have our benzylic carbon, and then we have a nitrile coming off of the end. Well, how could we make this compound? If we think about retrosynthesis, if I want to make a nitrile, I know that if I had benzyl bromide, if I had this compound, I could just do an SN2 with sodium cyanide. Right, this is just a regular old SN2 reaction where cyanide would be my nucleophile. It's going to displace the bromine as a bromide to give me the compound I want. So then the question becomes, well, how do I go from toluene to benzyl bromide? I do a benzylic bromination. How do we do that? We treat it with NBS. So we use N-bromosuccinimide and we heat it up, and that is going to give us benzyl bromide. Now that we've got our benzyl bromide, which is a very strong lacrimator, we take that and we treat it with sodium cyanide, and our cyanide is going to act as a nucleophile, do our SN2, and that's it. We're done. We have the desired product. The next one involves some SN1 chemistry, and SN1 chemistry doesn't get enough attention, I find. And there's reasons for that. It's not as synthetically useful as SN2. But what if we have a substituent on an aromatic ring? What if we've got a cyclohexyl group on here? So this would be cyclohexyl benzene, and we want to make this compound where we add a methoxy group. So we've still got our cyclohexyl group here, but we've also got a methoxy group here. Oh, I put it in the wrong spot. Mr. Dion's making Texas carbons here. I'm really, I think I'm probably just as tired as everybody else. So let's see. There we go. That looks a little bit more reasonable. Something like that. Well, same rationale. We looked at if we had a tertiary benzylic bromide. So if we had this compound where we have our cyclohexyl, and if we had a tertiary alkyl bromide, then we could just do an SN1. So if we treated this with methanol, it would just do an SN1 to give us the desired product. Well, how do I get from here to here? It's just a benzylic bromination. And so in the first step, I'm going to treat this with NBS, and I'm going to cook that up. That's going to give me this intermediate that I want. I have my aromatic ring, I have my cyclohexyl group, and I have my bromine. And this is tertiary benzylic. And then this is going to undergo an SN1 solvolysis reaction in methanol to give me the ether. And the last one that we're going to do for today is 17.18D, or 17.18E rather, where we're taking cumene or isopropyl benzene. So this compound here, this is called cumene. You could call it isopropyl benzene either way. And we want to make acetophenone from cumene. How would we go about doing that? Well, you can see that we lose a carbon somewhere along the way. And how would we go from having 6, 7, 8, 9 carbons to 8 carbons? You know, one way I could think about doing that is if we had this alkene, if we had the double bond here, then all we would have to do is an ozonolysis reaction, ozone followed by treatment with DMS, and that would give us the ketone. Well, how do we get from here to here? Well, I'd say we could do a number of things to produce the alkene. I think one of the easiest ways would be to do a benzylic bromination to start. So treat this with NBS and we heat that up, and that will give us a bromine in this position. Then we can just do an elimination with a hindered base. I mean, you could even use sodium methoxide here since this is a tertiary alkyl halide or benzylic halide. So you could treat that with, you know, sodium methoxide. It won't do any substitution, that's for darn sure. And that's going to give you the alkene that you want, this alkene. And then all we have to do is treat that with ozone in the first step and DMS in the second step, and we're done. We've made acetophenone.